Hey guys, the objective of this video is to find the decompression point for the section we've been working with. So I've just redrawn the section. 100 by 200, 15, 185 is where all of these centroids of the steel layers are. So what is the decompression point? The decompression point is the next point on our strength interaction diagram. So the decompression point, it says here, let me try to zoom in a bit for you guys. So it says here, the decompression point is calculated taking the strain in the extreme compressive fiber to equal 0.003, the strain in the extreme tensile fiber equals 0, and using the rectangular stress block given in clause 10.6.2.5. Okay, so this decompression point is from 10.6.2.3, so that's where it's from, and it says that the strain in the extreme compressive fiber is 0.003, and the strain in the extreme tensile fiber is 0. So the strain diagram is very simple. Here's the strain diagram. We've said that in the previous squash load video that this is in tension and this is in compression, and the reason we said that is because there's more steel layers here, which indicates that that's going to be taking tension and that's going to be taking compression. So now you can see the relevance of this. And it says that the strain in the extreme compressive fiber is 0.003, and the strain in the extreme tensile fiber is 0. So it's a very simple strain diagram. We're going to be getting to stresses in a second. So you've seen in the introduction video that we have this general layout here. Okay, so the distance from the extreme compressive fiber to the neutral axis is normally given by KUD, where D is the depth of the section. But in our case, KUD actually equals D. KUD, so you can see that the neutral axis for us has shifted all the way to the bottom. So KUD equals D. So we can say that this distance is KUD, which equals D. So that's just a special case for the decompression point. Normally that wouldn't happen, but because the decompression point has the neutral axis, or has this at 0, it makes KUD equal to D. So let's go ahead and work this stuff out. The stress thing, so the stress picture, so we're going to have once again our equivalent stress block. So it says in the decompression point that the equivalent stress block can be taken from clause 10.6.2.5. So that is just over the page where it gives you the values. So just like before, so the actual stress is alpha 2 FC dash. So that's given there, where alpha 2 is ranges. We're going to come to that in a sec, and it's the distance gamma KUD. Okay, so it is the distance it acts over is now gamma KUD, which in this case, because KU equals D, it's going to be gamma D. Okay, we're going to see how to find that in a sec, and then we're going to be able to find all the compressions and all the compressions of our steel. So let's go and do this now. For the concrete first. So for the concrete, the compression in the concrete is always given by stress times area. It's the same as a force. So the stress we need is alpha 2 FC dash. Okay, so that's the actual stress, where alpha 2 is equal to this term over here. So alpha 2 equals 1.0 minus 0.003 FC dash, where alpha 2 has to be between 0.85 and 0.76. So solving for this, 1.0 minus 0.003. Our FC dash, we've said in the first video, is 50 MPa. So FC dash is 50. And if you were to work this out, you would find alpha 2 would equal 0.85, which is between our range. That's good, that's fine. Now the next thing we need to find is gamma. Gamma is given by 1.05 0.5 minus 0.007 FC dash with this range there. So alpha equals 1.05 minus 0.007 FC dash, where alpha is between 0.85 and 0.67. Solving for this, FC dash is 50. You would find gamma would equal 0.7, which is between our range. So now we can go and find the compression in the concrete. So the compression in the concrete is the stress, which is alpha 2 FC dash, times by the area. Now the area is going to be this length here, so gamma D, times by the width of our concrete, so times by B. So we saw that in the introduction video, this picture here, alpha 2 FC dash by B by gamma KUD. Once again, our KUD equals D, so it's just given by gamma D times B. So that would be the stress. So we're going to work it out now. So alpha 2 is 0.85, FC dash is 50 MPa, times by gamma, which is 0.7, times by D. So D is 200, times by B. B, the width, is 100 mils. So if we were to work this out, you would find that you would get a value of 595 kilonewtons. Alright guys, I'm going to continue this in the next video where we're going to be doing the same for the steel. We'll see you there.